Hello, I'm David, and so we'll be doing 5 examples of how to identify if a molecule is polar or nonpolar. And first we'll go through some steps of how to do it. The first step is draw the Lewis structure. This will help us identify where the bond dipoles and what the shape of the atom is. The second one is identify the structure. This will help us out in knowing which one's polar, nonpolar, what direction the bond dipoles go, which one's is more negative than the other, etc. And the last one will be the answer. All right, the first one is sulfur trioxide. And first is the electrons. There's 3 oxygens, so it's 6 times 3, which is 18. And then 1 S, which is another 6, for a total of 24. And then for the Lewis structures, there are 3. And was 1, but it has resonance structures. So we see right here that it's a -1, 0, and -1. So all of them are exactly alike. But so since there's not a big difference, it doesn't matter which one you choose, it will all have the same. So they're interchangeable. We can also see that the bond dipoles pass over from sulfur to oxygen. Therefore, meaning that it pulls away from sulfur instead of into. And so that means the domain is trigonopyramidal. It's trigonopyramidal. So that means that there are 3 domains, and since they're all the exact same, they all cancel out. So they're all 3 from sulfur are oxygen, and they're all pulling in different directions, and they cancel, which makes it a nonpolar. It's nonpolar because all the bond dipoles cancel since they're all 3 of the same. Because of that, there is no net pull, so it makes it polar. Nonpolar. The next one is oxygen 2 fluoride. And the atoms, electrons, are 20 in total, which 6 coming from oxygen and 14 coming from fluorine. The Lewis structure is as follows. And this one does not have a resonance structure since there can only be one way of making it. And we can see that it has 1 and 2 domains, so it's not linear because you have to count these 2. Because of those 2, it makes it bent, which is the domain is actually tetrahedral, but the molecular is bent. Okay, so the answer is nonpolar because, you would think it's nonpolar, but it's actually polar, not nonpolar. So you can see because not all 4 are the exact same. 2 are fluorine, 2 are from the oxygen itself. So you could say that, oh, they're all pulling in different directions, but no, that's a common mistake people can make. Just because on the Lewis structure it looks like it's all aligned, so these 2 would cancel each other and these 2 would as well, it's not. Because if you remember that the tetrahedral shape does not mean do not align and will not cancel. You can see right here that they're all not on top of each other. So this one is not on top of that one, so they don't cancel out, as well as these 2. So because of that, it's actually a polar molecule. Also, the bond dipoles don't contribute to being polar because they don't cancel out. They only pull in one direction compared to the oxygen itself pulling a different direction. And fluorine, the pull with the fluorine, has a bigger strength than the one with the oxygen. All right, number 3 is 2 chlorides and a beryllium. And that has a total of 16 electrons. 2 come from beryllium and 14 from chloride, since there are 2. The Lewis structure is only 1. There are no resonance structures, and as you notice, beryllium doesn't have 8 electrons around it, because if you remember, beryllium is one of the few that does not obey the octet rule. Just like boron, it can have only 2. And in this state, beryllium atom has a formal charge of 0, as well as the two fluorines. Then you can see that the molecular geometry is linear since there's only 2. And if we remember from the chart, the linear, when it has 2 identical domains, is nonpolar. So because of that, the bond dipoles cancel out and makes it nonpolar. Right? Number 4 is, so you can see, and the electrons total out to be 32, 4 coming from carbon and 28 coming from chloride, which is a total of 32. And if we go to the Lewis structure, sorry, I messed up there, you can see that all of them obey the octet rule, with each having a formal charge of 0. But because of that, that means that they must participate in partial charges. The chlorines, all 4 of them, have the partial negative, and carbon has the partial positive. So, but because this is a tetrahedral, both in domain and molecular geometry, we can remember that since they're all exactly the same, and the formal charges cancel out, as well as the bond dipoles, since they're all pulling in different directions, but they all have the same amount of pull, it does not move, and it makes it nonpolar. We can remember from here, when 4 domains is when they're all alike and it's a tetrahedral, it's a nonpolar. And the last but not least is the ozone, which has a total of 3 oxygens, making 18 electrons. And as for the Lewis structure, it can have up to 2 because it has a resonance. And either or, you can see that it will have -1, +1, and 0. As well as here, 0, +1, -1. And if you add them up, the formal charge is 0, so it is at a good state. And you may think it's also linear, but you have to remember this right here makes it bent. The domain geometry is trigonal planar, but because this is not a different these are just non-bonding electrons, it's bent. And since they're all the same, they're really, you can't do a bond dipole because it's the exact same element. So the bond dipoles do not exist. But because these two are alike and this one isn't, it makes it polar. We can remember from here. Because one of them is not like the others. This one has a different pull compared to these two. So it pulls in the opposite direction with a different length, making it polar. Some common mistakes that happen as follows is because on the Lewis structure it looks like it's linear, we might misidentify it and think, oh, it's nonpolar since it's linear. But you have to remember these non-bonding make it bent, and they're also different compared to the 2 fluorines, which make it polar because they're different. Another common mistake is doing the resonance structure wrong, which can lead to one of them being completely wrong. Let's say this one might be, all 3 of these might be +1 and this one -3. If those, you have to make sure that the formal charges add up to a 0 in order to make it a good structure. If not, it will not result in a good example, making it either from nonpolar to polar. Another thing that can happen is if you forget your structures. If you get your structures and just think that this, well, if you forget your structures, it's going to be a hard time since you won't know which one cancels which. As you can see from here, if you forget that a tetrahedral with one different pair cancels out the other 3, you won't know. You might confuse it from nonpolar to polar. That can happen. Well, again, thank you for watching. This is David.